That's what I want. All right, so we're just going to extend what we talked about yesterday. We're going to kind of focus on the last couple ideas there. Use the rational root theorem and the irrational root theorem. Now, I'll be honest, the rational root theorem is something that's kind of outdated because we have graphing technologies that we'll use. But we're still going to talk through it, and we're still going to learn a little bit about it. Okay. All right. There is some merit to it, so we will spend a little time on it. All right. And I have to get this started here. All right. Now, not all of polynomials are factorable. Remember back in chapter 2, we had to use the quadratic formula to solve some of them. We also used completing the square to solve some. But if it's factorable, okay, it has what are called rational roots. Now, a rational root is something you can write as a fraction. Okay. Now, there's something called the rational root theorem that can help you find all the possible, notice it's possible, rational roots of a polynomial function. Possible means these are the ones we would try to synthetically divide by. All right, what's going on here?
It's freaking out.
Yeah. Okay. But everything was showing here. Anyway, basically it means those would be the numbers we would try to synthetically divide by to find factors. Okay. Now, we're not going to have to use a lot of synthetic division. We still use some, but we can use our graphs to help us. And we've done that before, haven't we? Using our graphs to help us find zeros. Okay. All right. So basically, if we're looking for the possible rational roots or possible rational zeros of a polynomial function, it's based off of two things. All right. The leading coefficient and the constant. Okay. So if a polynomial p of x has integer coefficients, which ours do, then every rational root of the polynomial can be written in the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. All right, so basically we're going to go, and I kind of maybe have this written. Oops, I'm trying to erase here. I'm going to write it the other way around. Basically, we're going to be looking at factors of our constant, they call those p, over the factors of the leading coefficient. All right, this will make more sense once we look at an example. Maybe it doesn't make a whole lot of sense right now. All right. Right. Well, if you think about it, and I'm just going to try to make a little more sense for you. One of the methods we used to solve quadratics in chapter 2 was factoring. And do you remember talking about something called the AC method to factor? Do you remember? Well, basically the AC method, if you don't remember, that's fine, was putting those two together. Well, isn't C the constant? And isn't A the leading coefficient? Right? So we did some factoring using A and C, so hopefully that's why we use those numbers. Okay. Now the first one we're gonna look at for this is we're gonna look at an application here. So, right, within this application, we'll talk about the rational root theorem. So the design of a box specifies that its length is 4 inches greater than its width. The height is 1 inch less than the width. The volume of the box is 12 cubic inches. Okay. Well, how do we find the volume of a box? Come on now, basically, length times width times height. Now, we don't know the length and the width and the height, but we know some relationships here. The length is 4 inches greater than its width. So that means our volume is going to be width plus 4 times width times height. The height is 1 inch less than the width. Well, would the height be W minus 1 then? Right, that's not a very good one, so I better make a better one here. Okay. And they also told us that the volume is 12. The volume of the box is 12 cubic inches. Okay. Well, that's going to help us figure out what the width is. Okay. We're going to have to figure out what is the width. Right. And we're going to have to do some multiplication and multiply things out. All right. So we'd have W plus 4 times W minus 1. Right. I'm going to do this right here. That would be W squared plus 4W. And that's just distributive property, guys. And W minus 1. Could I use FOIL to multiply these two? Certainly could. Well, it's going to be W cubed. Oops. First, I'm going to go inside, outside. I should have went the other way around. Sorry about that. Okay. So basically, when all's said and done, we have W cubed plus 3W squared minus 4W equals 12. Right? These two we can combine and get 3. All right, everybody with me? Now, generally, if we're going to try to solve this for W, we're going to set it equal to 0. So right now, this is where we stand. Okay, that's where we stand. That's the polynomial we're going to solve by factor. Once again, it took a lot of work to get there. Okay, it took a lot of work to get there, but you know, that's the work we had to do. Okay, so I'm going to write this on the board, and then I'm going to go to someplace I can write on the iPad, just so I don't write down the wrong thing. Okay, so I'm going to take this. Whoops. And I'm going to make a whiteboard here. Okay, so how the heck can we solve this? Well, this is what we're trying to solve. 0 is W cubed plus 3W squared minus 4W minus 12. Now, this is where we can use that thing called the rational roots theorem. Okay, all of the factors of the constant, the factors of the constant is 12. So factors of 12 compared with factors of 1. 1 is the leading coefficient, right? Well, isn't that just going to be all the factors of 12? So what are some factors of 12? Give me some factors of 12. Should be easy, guys. Okay, I'm going to say plus or minus 3, plus or minus 4. What are some others?
2 and 6.
All right, plus or minus 2, plus or minus 6. We have two more. 1 and 12. Now, if we have, I said if we have any rational roots, it's going to have to come from this list right here. Once again, I said if. There's no guarantee we're going to have rational roots, but if we have them, they're going to have to come from this list right here. All right? Now, rather than synthetically dividing this polynomial by all of those numbers, I want you to graph that red polynomial for me and see if any of those possible rational zeros are actually rational zeros. All right, so why don't you do that for me, please? All right, so yes, you're going to have to graph on Desmos. So this is where we're using technology to help us. I don't want to synthetically divide by all those numbers because that would take a whole lot of time and a whole lot of paper. So we're going to see if we have any values where it crosses the x-axis. I think 3 of those should work. All right, 3 of those numbers should work. Everybody agree? If you look at it, 3 of those numbers work. Now, that's not always going to happen where, you know, this one is a third-degree polynomial. It can only have 3 solutions, right? It just so happens that all 3 are rational. All right, I think we get these numbers. -3, -2, and I'm going to say W. I better say W here, sorry. And W is 2. Now, in the scope of this word problem, there's no way this could be or this could be, right? The width of a rectangle, or excuse me, the width of a box can't be negative, right? But we're solving a polynomial, so we got to bear with it. What that really means is if we were to factor this out, we'd have W plus 3, because -3 makes it 0. W plus 2, -2 makes it 0. And W minus 2. So since these two make no sense in our problem, because we can't have a negative width, I think the width of our rectangle would have to be 2. Right? Now, if this wasn't a word problem, we'd have 3 solutions, right? But it's a word problem where W represents the width of a box. So there's no way we would consider negative values. Because you can't have a negative length of a box. You can't have a negative volume and such. Okay? Any questions on that? All right, so we used the polynomial we built along with the possible rational zeros and Desmos to help us answer that question. Okay? Do you have any questions on that? Like I said, I'm gonna say this again, and I'm not gonna demean the importance of this, but since we can graph, is this really very important? Those possible rational, it's really not as important to you as it would have been years ago when we didn't have graphing technology. Does that make sense? Because you can actually physically see where they are. And I encourage you, use your graphing calculator to do that, right? But the underlying reason is, you know, we can build a list, right? We can build a list. Okay. All right. We're gonna go back to the PowerPoint here. Give me a second here. And once again, if you know, they used X, that's fine. That's the exact same thing we had right there, isn't it? And then we solved that, right? So if you look at the PowerPoint, we basically solved all that. We used W instead of X, whatever, doesn't really matter. Okay. Yeah, polynomial equations may also have what are called irrational roots. Irrational roots can't be written as a fraction. All right, when you think of irrational roots, okay, for me, when I think of irrational roots, I think of like square roots a lot of times. For example, like the square root of 3 isn't a rational number. Okay. Now, if we have irrational roots, those roots have to show up in pairs. Right? So the polynomial p of x has a rational coefficient, and a plus b squared of c is a root of the polynomial equation. Then a minus b square root of c is also a root. Okay, so irrational roots must show up in pairs like this. Okay. Irrational roots have to show up in pairs. Didn't imaginary roots have to show up in pairs? Back in chapter 2? They did, right? Well, here irrational roots or zeros have to show up in pairs also, right? Now, we can see them on our graph, but we're not going to be able to find them exactly. We want to write them in a form like this. We want to be precise. We don't want decimal approximations. We're going to find these values exactly. All right, and there's a process, and it really includes everything we've talked about so far in chapter 3. So how the heck do we find this? Well, we're going to use this one as an example, okay? So if I was trying to identify all the real roots of this polynomial, and I want to find them exactly, and I want to find the exact value, here's what I would do, and I'm going to have you do that for me. Graph this for me. See if you see any real roots. Okay. Graph that. See if you find any rational roots. Any numbers that are nice, neat. We can write them as a fraction. And a third-degree polynomial could have 3 roots. Is one of those a nice number right there? Yeah, that one right there. That's not important really. But yeah. Did you find a nice number that we can write as a fraction?
Yes.
1/2, right?
Yes.
So our nice root is that x equals 1/2. Now, would you agree there's 2 other ones? There's 2 other ones. Now, those 2 are an irrational pair, like we just talked about. They are irrational. All right? Now, here's how we find those using an exact science here. Well, what does it appear I'm setting up here? What does it look like I'm going to do here? Yeah, I'm going to use synthetic division. And you know what? I know, I'm going to be so confident, I know this has to be 0. Why? Because you guys all graphed it and said it was 0, right? Well, here we go. It's going to be a half, -8. Half of that is -4. -4, half of that's -2. So we were right, correct? So what that means is we are this close. Oops, I got to back up a minute here. We are right here as far as completely factoring this polynomial. Okay. Stop there for a second. Now, just to review, where did all of this come from, guys? Did I just make that up? No, it came from right here. All right, so we often said that last line has meaning, excuse me. Okay. Well, if those other 2 roots are irrational, that means we should be able to come up with the solutions for those using, since this is a quadratic, we should be able to use the quadratic formula. Right? Now, I'm going to try to make my life a little easier here, because I recognize that all of those are divisible by 2, so I'm really looking to solve this. Is that going to make my numbers smaller and just easier to work with? If you use 2, -8 and 4, or -4, that's fine. You're going to have more simplifying to do in the end, so I'm going to simplify it right now. Well, here we go with the quadratic formula. The opposite of b plus or minus the square root of -4 squared, which is 16, minus 4 times a times c, all over 2 times a. Okay? Now, when we see that plus or minus the radical, does that kind of tell us it's going to be a pair because of that plus or minus? It does. All right? So then we're going to have 4 plus or minus the square root of, well, that's going to be 24. All right? This is 16 minus a -8, which is like 16 plus 8 over 2. Okay? Everybody good with that? Well, now that's going to be 4 plus or minus 2 square root of 6 over 2. 4 is a perfect square factor of 24. 4 times 6 is 24. The square root of 4 is 2. So I think our other roots, if I simplify, will be 2 plus or minus the square root of 6. There's our 2 solutions that we got that are irrational. There's the one that was rational. Okay. Now, I'm going to ask Devin. Devin, what's on Desmos? What do you get for 2 plus the square root of 6? Approximately as a decimal.
4.49.
Now, was that one of the other ones you saw in Desmos?
Yes.
4.49? And do you think the other one is going to be 2 minus the square root of 6? Yeah, that'd probably be negative 2.29, I bet. All right. Now, which means we can kind of check things, but these are the answers we want right here, guys. We want the precise value. We don't want it rounded off decimals. We want to find things exact. Okay. So let's look at what we did. We graphed it, and we found a nice rational root. Right? We synthetically divided so that we could factor it out a little bit, and then we used the quadratic formula. Right? Is that really building on combining a lot of things we've worked on this year? It truly is. Right? It truly is. So trust the process, and this process will work not only in section 5, but it'll work in section 6 when we move on there too. Right? See what goes on here. Now they built a list of rational roots. We didn't do that because we said, heck with that, we're going to graph it, right? Graph it. The intercepts were those numbers, right? And once again, which one did we use? This one. Okay. We made sure it worked by synthetic division. And we kind of knew it worked because the graph told us it was going to work, right? Then we factored it like so, right? And then we found the remaining roots by using the quadratic formula. Took out a factor of 2 to make things easier for us. And then use the quadratic formula, and that's what we got. Okay. So I'm not saying it's a quick, easy process, but chunk it into smaller little pieces. Graph it. See if you got any nice rational roots. If you get one, synthetically divide. Okay. If you get 2, synthetically divide. Whatever. Okay. We may have to, in order to find irrational roots, we may have to use the quadratic formula. Okay. Probably gonna have to. So here's another one. We're gonna work on this together. So I'm gonna ask you, what should we do first? Graph it. Bingo. Graph this one for me, please. The graph should point us in the right direction. I think you're going to find one nice number that works. I should say a rational number that works. And once again, we're doing this work together, but down the road, you're going to have to do this. I can point in the right direction, but I'm not going to be sitting over your shoulder making sure you do all this. All right, did we find a nice rational 0? Negative 1/2? Everybody good with that? Now, if you didn't get negative 1/2, you maybe typed it in wrong. Once again, we're not really going to use the rational root theorem. We're going to say, I graphed it. Oops, sorry, went too fast. And negative 0.5 worked. The others were about negative 1.2 and 3.2. Is that right? So once we get a nice rational root, what do we do with it? Now we're going to divide by that. Exactly. We're going to divide by negative 1/2. Okay. And once again, what should the remainder be? The graph told us it should be what? 0. So if it's not 0, we made a mistake. Looks to me like it's going to work. All right. So in factored form, it's going to look like that. Well, I think this looks very similar to the one we saw before. We better take out a common factor of 2. Once again, you don't have to, but it's going to make your life easier in the long run. Factor out of 2 is going to make the numbers more smaller, easier to work with. Use the quadratic formula, and we get 1 plus or minus the square root of 5. Well, I just happen to know the square root of 5 is about 2.23. So what's 1 plus 2.2? 3.2. And what is 1 minus 2.2? Negative 1.2. Yeah. Any questions? Okay. Once again, that process we talked about here today combines a lot of ideas we've talked about throughout the year. Right? And we're not going to just learn this in section 5 and it's going to go away. We're going to use this in section 6 and section 7. So, give it a chance. It might take a little longer to sink in for some of us than others. I mean, that's going to happen. Right? But use Desmos, use synthetic division, and we're using the quadratic formula quite a bit. All right. Now, Monday, we're going to have a worksheet. We're going to go over this stuff again on Monday. Okay. But you need to spend a little time on some questions from this lesson. So there's some exercises to work on for Monday. Like I said, Monday, we won't learn anything new. We'll review this process with a couple questions. Then you'll have a worksheet that we will go over on Tuesday. Okay. All right, so make sure you're doing what you need to on your end.